and we're going over 3.2. This is the gamma lesson. It's the end of the section 3.2. And in the textbook, we're on page 192, where it says interpreting computer regression output. So what's going to happen is you are accountable for this in May, where you're going to get this software output, and you're going to have to sort through the clutter and find the values that are important to you. So if I'm looking on page 192, they've got two software. They got Minitab and this JMP. And they're all going to give you, they're going to give you more information than your calculator, and you have to sort through the stuff you don't want. So if I'm looking at this thing for linear regression, the y-intercept is going to be referred to is the number after the constant. And the explanatory, the input coefficient, the slope, would be across from explanatory. Okay, so we're going to do a problem together. Well, you're going to do a problem. We're going to go over it, where you have to interpret this software output. It's not a big deal, and you'll get plenty of practice. It's primarily for linear regression, but other things also. And we actually have a supplemental book to give you in the spring that has an entire chapter on software output, so it won't be a big deal. Okay. Regression to the mean. Okay, now this is copied and pasted from the beta lesson, except you notice over here, this is new. So it's another way to calculate the slope. The slope is going to be the correlation coefficient multiplied by the ratio of the standard deviation of the response variable to the standard deviation of the explanatory variable. Okay, this will give you the slope. So it's like an algebra 1 problem. You've got the slope, b sub 1, r, s sub y, and s sub x. You've got 4 unknowns. You conceivably get a problem on the AP test where they'll give you values for 3 of them. So it's just about solving for the one that you don't know. Okay, so these are both equal to the slope, but this is what you would be assessed on, whether you could do that. All right? And regression to the mean is explaining something such that, like if you think in terms of sports, you think of the sophomore slump, and people that have like a big first year often have a tough second year. And there's a statistical explanation for that. It's regression to the mean. Like if you was trying to think of somebody, and the person that occurred to me was Juan Soto. That's only going to mean something to most people in the room. But Soto is the player who essentially replaced Bryce Harper in Washington. And he played really well as a rookie, and they won the World Series. Now, it didn't look like Soto regressed much. He looked like he was equally effective this year, which would just mean that Soto is potentially an outlier, that he's not affected by regression to the mean. But most people are going to regress. Mean pulls you in. It's powerful. It's like a magnet. Okay? And then it's another way of expressing y hat. So we're going to just pause the video, and you're going to go to 2 questions. 61, where you have computer output, and answer questions about that, and 67, where you get a scatter plot. So you're going to do one of each. I will tell you ahead of time, there are no assessment questions on computer output. So I didn't put them on the test on Thursday. But we're going to go over that. I'm going to give you time to do those 2 questions, and then we're going to come back to this. All right, so we're going to go over this. And I'm looking at 61, okay? So I took what was in the textbook, I pasted in this table. And the bold are the numbers that you're looking for to answer the questions. Okay? So in this problem, they're telling you that the wind speed depends upon the temperature, which might seem a little questionable to you. So we'll see how it works out. The wind speed depends upon the temperature. And I'm looking at this thing here, and the way that this software output is given to you for 61 across from the intercept. Just literally, it's the intercept, right? And then the average temperature, well, that's going to give you the slope. So I took these values and put them in Y1. And question A says, find the residual when the average temperature is 42. So if you put 42 into the regression equation, you get this output, about 10.2 miles per hour. Except what? The actual value on that day was 2.2. And a residual was observed, and 2.2 was observed. Take away expected. Expected is what you got out of the regression equation. So the residual is negative. That's important. The SIGN of the residual matters. I mean, you get a multiple choice, and they're going to give you both signs. So what happened? The least square regression overestimated. It told you a wind speed of this when it was that, and the negative residual is telling you you're below the line of best fit. B is important. Interpret the slope. So I'm looking at this slope. Now, I did a size change of magnitude 10. Don't worry about that. You don't have to do that. But I'm saying for every increase in 10 degrees, the wind speed tends to decrease by 0.4 miles per hour. If you said for every increase of 1 degree, the wind speed tends to decrease by 0.04 miles per hour, it's the same thing. But what's important in this answer is tends to decrease. Okay, you just saw how much it was off by at 42. So you got to be careful what how you write this. How much the actual wind speed typically vary. Now, when you see that term, typically vary, you should make a connection that is standard deviation. So I go here up to the output. The standard deviation was root mean square error. I mean, it's kind of disguised in there, the terminology, and all these software outputs all have different language. You've got to find the number that applies to this. So what is that telling you? The average residual. It's typically off in a height, and the height would be the wind speed, by between 3.5 and 4 miles per hour. And then D's kind of a layup. They're leading you to this and saying, because we gave you this definition on Thursday that you are accountable for memorizing. The definition of R squared is the proportion of change in the output that can be attributed to change in the input. And in this case, the output is wind speed and the input is temperature. So what now, what percent of the variability, which is a synonym for change, in average wind speed is accounted for the least square regression line. And that's the R squared value, which they tell you is essentially 4.8%, which is very low. Well, yeah, I mean, you wouldn't expect that you could predict the wind speed from temperature. So that's telling you less than 5% of the change in the wind speed can be attributed to the change in the temperature. Okay? And now going to 67, you've got this scatter plot. And the one child is here. So this child was 5'11", and they jumped 35 inches vertically. Their red dot is separated from the others. It's a potential outlier. So what influence does he have on the least square regression line, which we don't even have? Now, the answer, I'm saying Jake is in quadrant 1. What does that mean? Well, it's this. If you have these data points, with this. You have these data points. And then you have the grand mean, which is the mean value of the inputs and the mean value of the outputs. And if you were to draw axes through the grand mean, here's quadrant 1, 2, 3, 4. But in quadrant 1 and quadrant 3, ready? Look at quadrant 1. Your residuals for X and Y are both positive. They're greater than 0. So when you multiply them together, it'll be greater than 0. In quadrant 3, they're both negative. When you multiply them together, they're going to be greater than 0. And that's why if you have points that are essentially mostly in quadrant 1 and 3, R is going to be positive. Well, you're going to have a positive slope. And here the SIGNs are different in 2 and 4. You'd have a negative slope. So here, the grand mean is going to be in here somewhere. But the red point is to the right and up from there. So he's in quadrant 1. Positive residual for the input and for the response. His data point increases the positive slope. Now think about this. This red dot is pulling the line up. So he's decreasing the y-intercept. If you take this red dot out, you remove it, this line's going to fall. It's like a seesaw. And when it falls, the y-intercept's going to go higher than it is right now from like 11. Okay? So he has a large residual. What's going to happen? Well, he's going to decrease R squared. Think about that. R squared is telling you how much of the change in the vertical jump can be explained by the change in the height. He's not near the line. So he's decreasing R squared because the line didn't do a good job to predict how far he would jump. Okay? So